Thanks, Michael. Now we'll start with our presentations from the forecasters. First, we will be talking about the new mesocyclone detection algorithm, or NMDA, with Mike Seaman from WFO, Salt Lake City, Utah. Go ahead, Mike.
All right, thanks, Lisa. Basically, what I'm going to talk about is the new mesocyclone detection algorithm. I spent some time kind of comparing it to the operational version that we currently use. And in general, this week it did a better job of identifying and tracking mesocyclones within convection. There were some pitfalls, and I just want to kind of point out a couple of them. This is the QLCS that moved into the St. Louis area on Tuesday. And as we look through here, you can see a couple of things. Up on the northern part of the line, you can see several spurious NMDA detections of mesocyclones that were likely just associated with spurious velocity, not really legitimate couplers. So the new algorithm did seem a little bit sensitive with that. But what I really want to focus on here was the embedded supercell that was approaching St. Charles here in the middle of the screen. You can see a very nice inflow notch there. And the mesocyclone detection algorithm, the new one, took a little time before it actually identified that feature. So what we're going to do now is basically step through about 30 minutes before the new NMDA actually identified that feature. To the southwest, or in the upper right corner of the screen there, that top left image is reflectivity at half degree. And you can kind of see in the bottom portion there the inflow notch. If we step upwards, we go up to 4 degrees, you can see a really nicely defined bounded weak echo region. And when we step up to 8 degrees, we've got 70 plus dBz overhanging that bounded weak echo region. So very obviously a supercell in progress there. However, the new mesocyclone detection algorithm did not pick up on that until about 30 minutes later. In fairness, the operational version did not either. We think it has something to do with the lack of reflectivity within the updraft region that is basically getting it those mesocyclones filtered out. So that's basically an example of one of the pitfalls and basically things to look at, and always fall back on the base data. So takeaways from this example were basically the new detection algorithm did not identify and track the supercell heading into St. Louis until it was about 10 minutes out. It was slow to detect that despite the obvious characteristics, and the new NMDA was also rather noisy at times with identifying mesocyclones along the advancing QLCS. But I will again say that it did, in general, do a better job than the current version.
Thanks, Mike. Next up, we will have John Bangoff from WFO State College, Pennsylvania, and he will be talking about the conditional probability of tornado intensity product. And he will also be using the same case that Mike looked at. Go ahead, John.
Thank you so much, Elisa. So we will be looking at the same St. Louis case, and this was after the tornado had formed. So you'll notice on the top left there of this image is reflectivity, velocity top right, correlation coefficient bottom left, and differential reflectivity bottom right. Very clear tornado debris signature with 65 dBz reflectivity, and that significantly reduced correlation coefficient evident at the TDS bottom. So one of the things that I wanted to do with looking at this conditional probability of tornado intensity this week was compare it to another proxy for tornado intensity in real time, the TDS height. So there's been plenty of research done on this over the past several years, and in fact on this tornado, you can see in the bottom left image, bottom left panel of it, the correlation coefficient. It's a little hard to see where that lowering occurs, but it's about the 10-degree elevation scan, gets up to about 10,000 feet. Previous research has shown that that's about an EF2 tornado. So then we go ahead and look at the conditional probability of tornado intensity, and that is plotted on the right image in the top left pane. And this CPTI basically has 3 different fields that it plots. It's got the probability of a weak tornado, probability of a strong tornado, and probability of a violent tornado. And the way this works is basically it's a summation. All of those 3 probabilities add up to 100%. And so when you get a reduction in the weak tornado, it means there's a higher chance of a strong tornado, violent tornado, etc. And so on this particular case, I also have plotted storm relative velocity. You can see a nice couplet, the MRMS rotation tracks, which we're pretty familiar with, and this low-level azimuthal shear. The bullseye's there, and in particular on this case, I think it populated about a 20 to 25% chance of a strong tornado. Now this is scale, basically 18% is what was fed into this particular model, so anything above 18% gives you some confidence that there could be a strong tornado. I believe this was surveyed as about an EF2. So this one did pretty well. I just wanted to show it since Mike had looked at it as well. I also have one more case study that we'll look at. This was in the far southwestern portion of the Tulsa CWA using the KTLX radar. And you can again see on the left-hand side a nice tornado debris signature. This one got up to about 6,000 feet. And so not quite as strong, probably be in the EF1 category. And it's a little hard to see. I don't have the values plotted, but this one also matches up with that. The CPTI, strong and violent, is plotted there. On the top left, the maximum percentage is about 18 to 20%. So a little bit suppressed, still seem to do a pretty good job. And I think this could be a really, really cool tool in terms of operations, being able to make decisions of impact-based wording, even potentially having some confidence as we go out and survey damage, what was the expected intensity of these tornadoes through the life cycle. So a really useful product and enjoy using it quite a bit this week. And then the takeaways, so again, excellent tool for characterizing potential tornado intensity in real time. And these TDS height estimates of tornado intensity, which have been studied for the past several years, match up pretty well with what we're seeing. Still need some calibration and training on exactly what those thresholds should be. And then again, the operational use is very obvious with impact-based warning decisions or increased wording and tornado warning updates.
Thanks. Now we'll move on to Corey Martin from WFO Des Moines, Iowa, and he will be talking about the Geostationary Lightning Mapper, or GLM. Go ahead, Corey.
Yeah, thank you. So like you said, I'm going to talk about GLM, and specifically I'm going to focus on the flash extent density product since that was used most extensively this week. On the left there, you'll see the flash extent density product from Convection that we watched on Monday. That's laid in unison with Earth Network's Total Lightning ground detection network. The problem that we did see with the GLM flash extent density product through the week, especially out in like the Texas Panhandle, is oddly low values at times that didn't seem to match what the ground network was detecting. So if you see that in motion there on the left, you're going to see the times where the flash extent density seems to drop out quite a bit, but yet our Earth Network's total lightning values remain about the same. So that really lowered our confidence in exactly what the flash extent density or the GLM was sensing at that time. However, we didn't really see the same problem the further east we went. When we got in more into Oklahoma and Kansas, it seemed like the flash extent density was working pretty well. So the subject matter experts that we had here wondered if it was issues with viewing angle and optical depth. However, as an operational forecaster, if I were to see these issues in real time, it would just lower my confidence in the product because I just don't have the expertise to be able to diagnose those issues with the GLM. And then on the right there, if you look in the upper right of the 4-panel, again, that's your flash extent density with your ground network lightning data. Again, we saw the same problem. This time you're seeing what looks like a lightning jump in the flash extent density data, but really, according to the Earth Network's data, our lightning activity remained pretty much the same. So if you weren't using these two products in unison, if you were just using the GLM data, you may have expected that your updraft there is strengthening significantly at that time, when in reality, that doesn't seem to be the case. And if we were to have reflectivity posted here, you would see a rather steady state updraft at that time. But however, here is a success story using the flash extent density. If you look in the upper right, you see the same thing, flash extent density plotted with the Earth Network data. And you see both there at the same time go through a lightning jump early in that loop where you see the values increase quite a bit. If you look at reflectivity on the left at the same time, you'll notice about 10-15 minutes later you see a significant uptick in your lowest scan of the reflectivity, which means that, yeah, the storm did strengthen a little bit after you saw that uptick in your lightning activity. So that could definitely be a good tool, in your warning process if you're trying to get a jump and some better lead time on severe convection. So again, just to summarize, we had routine problems with the flash extent density output through the week, but those seem to be concentrated out toward the Texas Panhandle High Plains region. Again, there are several hypotheses to why this could be a problem, but still that's an issue for the operational forecast if you want to make confident use of that data. But the flash extent density was very useful at times for detecting lightning jumps. I especially liked it because it provides a spatial display and not a numerical display. So really, if I'm just doing a quick glance over the data, it really jumps off the screen at me. There could be some adjustments to the color curve or maybe a delta product to see trends in the lightning data instead of just the raw values. That can make the product even easier for us to use on the operational side.